Hi everyone, this is the repair of a Keithley 225 current source which I recently acquired. It was working at the time I got it, but it had some accuracy issues, and I was thinking I would calibrate some of the internal voltages and set points for the various parameters like compliance voltage or crossover voltage, things like that that are important in a full 4-quadrant type of a current source. So anyway, I did something which caused it to break. That is, I blew up something. So I'm in the process of debugging what it is and trying to fix it. I haven't repaired the unit, and I've stopped at a point where I can show you some things that I've done and explain the working of this particular current source, which is very interesting. And we'll go through the repair process as I go along. So let's go over the front panel again. We're starting from the bottom left, the on-off switch, which is the mains AC control switch. The next potentiometer, this is the compliance voltage set from 10 volts all the way to 100 volts, continuously variable. Then the standby selection or the actual current output, either positive or negative, and in between you have the standby settings, in which case if it's in standby the current will not come out of the instrument but will be internally dumped into a load. You have a filter that allows you to filter some of the noise that may be on this, and this is the low and the high outputs. The low is in this particular instrument connected to the chassis at the back, and high is basically whatever current output you're setting. It can be either input or an output current. And then you have the 3 decade resistance decade settings. The most significant digit is here on the MSB, and then the middle and the LSB, the lowest significant digit. And you also have a fine control here in this knob, which is 0.02% of the full scale. So if you have a full scale reading of, let's say, 100, you can adjust this by 0.02% of that. Normally I keep it on the leftmost side, so this is at 0 position right now. Then the decade resistance sets the value of the current in various decades, starting from a minimum of 100 nanoamps, and the decimal point is indicated by these lights when it's on, all the way up to, there are 7 ranges here, up to 100 milliamps in this particular case, extreme right. So that basically describes the unit. It's fairly simple to operate, as you can see. You select the current you want based on these switches, and you'll get that output on this pin over here, terminal over here. Now if you want to restrict the output to 40 volts maximum, then you set it to 40 volts or 30 volts, in which case if the voltage, if there's no load, for example, if this is totally floating, the output will go all the way to this 30 volts and remain there, or minus 30 volts depending on the polarity here. But if it's operating in current mode with a suitably low resistance, then basically the current that is set here will show up in the load. So conceptually, Keithley 225, it looks something like this. On the left side you have a 1 volt precision voltage source, which is internally generated using a Zener diode and some resistors to create this 1 volt. It goes into a Kelvin-Wally divider, which is like a multi-stacked resistor network with several decade ranges. So you can go, as you can see on the instrument face, there are 4 dials, and they can be used to set the current in 4 decades ranges. And then the output of that divider, a Kelvin-Wally divider, goes into an amplifier which we call A1 over here, and there's another amplifier called A2 which feeds back the output of the current source, so that it basically senses the output voltage, and if it exceeds a certain value it will go into voltage mode, otherwise it will remain in current mode. and this is also to, in some cases, to protect circuitry that cannot handle certain voltages above their rated spec. So you can control that level using the compliance adjustment. The sum of these two amplifier outputs goes into A3, which then drives a couple of series regulators. One is a positive series regulator, one is a negative series regulator, and that is basically controlling a 130 volt and a plus and minus 130 volt supply. So the maximum output voltage that this can generate is actually 100 volts, but they have designed it to internally to handle or produce 130 volts. Overall, it looks fairly simple from the block diagram. The current output is going through the sum of these two, or actually only one is selected at a given time. So one of these will be active, and it goes through resistor decade, which basically allows you to scale the value of the current in increments of 10x. So starting from 10 nanoamps or so, it can go all the way to 100 milliamps, and that is selected by this resistor decade range switch, which is the fourth switch on this on the current source on the right side. There's also option to connect the low output to ground, which makes it connects the low to earth. So in case, but if you want it to be floating, you can disconnect the link, and then this becomes a floating output to drive a floating load. So that basically sums up this overall block diagram for this unit. So I will next go into the details about how this works, maybe going to a detailed schematic, and show you what I've discovered so far in terms of the failure that had happened, and describe how I'm going to go about fixing it. So next up is the schematic itself. This is page 1 of the schematic, or page 2 in fact, but I'll start with this page since it contains the power supply. So on the bottom left is your transformer with the input power plug. There's a transformer here which generates several output AC voltages. The first one on top is used to generate the 130 volt supply, plus and minus. The second one here below that is with these full bridge rectifier, generates a 10 volt supply, plus and minus 10 volts. And then there's also a third secondary turn, which is used to generate a 24 volt supply, which is then used to create special plus and minus 12 volt supply. This is the most critical supply in this particular instrument, and this determines the functionality of this instrument. If you look at the overall picture of how it works, these outputs here are basically reference to ground, that is the center tap of these bridge rectifier outputs are all grounded if you basically connect the chassis to the low output of this instrument. But this particular output here is called the common, which goes to the main circuit board, and the common is used to basically drive the output current into the load. This is actually around 0 volts, but it's not theoretically, or the way it's designed is not equal to the ground potential. So the common, around the common you have the plus and minus 12 volts that is generated using this full bridge wave rectifiers, creates around 25 volts or 26 volts to input of this regulator, which creates a 24 volt supply based on the adjustment of this resistor here, R226. That is of course referred to this lower supply voltage, ground, and that is then converted to a differential output in terms of polarity to a plus and minus 12 volt supply output using this amplifier. So this amplifier is biased, the positive input is biased at halfway between these two. So if this is 0 volts, this will be 24 volts. But the way it's configured, the feedback along with the way this is connected, this generates a a 0 volt at this point, and this becomes minus 12 and this becomes plus 12. Since there is no ground reference in this particular supply, that is, this is entirely floating, the ground is really determined by this amplifier, and this amplifier has to be able to drive this ground common, or the common terminal, all over this instrument to 0 volts and keep it there. And it's basically independent of the earth or the low ground, which is the output of this instrument. So if this amplifier fails, then basically nothing works. This output could float to anything, any voltage. It could go to 100 volts, minus 100 volts, or any voltage in between the rails that is generated by the plus minus 130 volt. Because if you look at the overall block diagram, the plus minus 130 volt reference common point is really the output of this amplifier, which is a common node. So in my case, what I think happened was, when I was probing one of the common node, I must have touched something. The probe must have shorted another terminal inside. I'll show you exactly where, and it blew up. I believe this op amp, and I think this regulator. I did measure. I have taken these two out of the circuit, out of the board, and I've measured them or tested them outside, and these appear to have failed. Returning to the schematic again, I showed you the power supply, the 130 volt, the 10 volt, and the 12 volt supplies. Over here in the left top is a compliance detector, voltage detector. It's a bunch of transistors, PNP, NPN, and they basically sense some of the voltages internally on the main board, which I will show next, and basically display or cut off the current source, or keep it in a voltage mode, or switch it to current mode, depending on what those voltages are. And it can also, of course, adjust those limits where they should trip. That is, if the voltage exceeds a certain value, then a light will show up on the front panel saying that you have reached the compliance limit, either positive or negative, and they are both here. And that is useful to know if you're checking what's happening with the instrument, and whether it's trying to drive too high a voltage or so. The three neon lamps on the right side are for the decade settings. So depending on whether it's 10 milliamps or 1 milliamp or 100 microamps, 10 microamps, different lights are lit by this. And this is again controlled by a switch on the main board, and these are all ganged together, and it's shown on this particular schematic. So here's the schematic of the actual current source, the main board, and I will go over the 2 or 3 main sections in here. If you look at the block diagram again, there's A1, A2, and A3, 3 amplifiers, which are built up of individual multiple stages and so on. The Kelvin Valley divider and the compliance adjustment setting, that goes into the series regulator. So in this particular, what you're seeing right now on the board is A1 and A3. A2 is not in the picture. So, and then Kelvin Valley divider. So let's look at these. So the Kelvin Valley divider is this big resistor network. It's controlled by the 3 switches, which can select different digits from the MSB down to the LSB, plus a fine tune, which is the final potentiometer, which is a variable one, which gives you the 0.02% full scale adjustment. So the output of this Kelvin Valley divider goes into this A1 amplifier, which is really this main amplifier here, whose output is whose second input is basically the feedback of the output that is coming from the current source load. So it compares those two, and then that is amplified by this match FET pair, goes into the second stage, A3A. Sorry, not the second stage, it's basically the A3 amplifier, which is over here, which is doing also taking the input from the compliance side, but we'll get to that later. So the A3A again is a differential amplifier with 2 inputs and a differential output. It's got a voltage limiting using these diodes on the output side, and that drives this PNP source degenerated type amplifier, which is the load is really at the bottom here. So that goes into this A3C stage, which compares the compliance voltage, whatever that is set by A2. So the A2 input comes in through this network, through the main switching network, because it can either have a positive or negative output. So it has to be switched correctly in here, and that is compared over here, and that output essentially then will drive through this network, the series regulator, which is not in the picture again. So the 1 volt is the precision 1 volt that is used to generate all the currents, and once you have a precision voltage and a very accurate resistor network, you can basically get any accurate current, and also that can be scaled by this decade resistance network, which is simply a bunch of resistors from 10 ohms to 10 mega ohms. So that gives you all the currents from, I think, 10 nanoamps all the way up to 100 milliamps. So now we'll go into the left side of the schematic, which shows the A2 amplifier, which is the compliance voltage amplifier, and the series regulators. Now we can look at the left side, which shows you the A2 amplifier and the series regulators. So the A2 is right here, and the series regulators are over here. So A2 takes the output of this, senses the output voltage right at the common node here, and on one side, and the other side is basically the whatever the switched in value that it's comparing, positive, negative, whatever. So if it's that's depending on this network here. So essentially it comes through here, and then it's looking at this input over here through this network. The output is basically going into this the other main power supply board, which basically senses what the voltage limits are, and as well as to set the trip points. So that's not on this board, but these outputs go into through this connector that's shown here. The series regulator are these main big transistors, the Q101 and Q105, which are TO66 package. I believe they handle like 20 watts or so. And then there are a bunch of other transistors which are used to control the biasing of this, to permit the outputs of these. That is the emitter of this and the emitter of this one. I'm sorry, the collector and the emitter of these two, since they are negative and positive voltages, they are combined through these 4 resistors. These are current sense resistors, and so they can basically tell you how much current. If this exceeds a certain current limit, it can shut down, and that is tied at the common node here. So that's exactly what we see in this one here, where they are tied together and they go out on the common node to the final output here. So so basically this completes the entire current source. And I think the next step is really for me to show you what I found and how I fixed it. There was some interesting follow-up to that as well, so let's go to that next. Before going into the final repair, I wanted to show you one of the changes I had to make because I couldn't get the regulators and the amplifier for the 12 volt supply. So as far as the regulator, I just used LM317, which is I think a 1 amp output regulator, and the 26 volts is really this floating supply that's coming off the bridge rectifier separate transformer winding, and then this I had to change, of course, the resistor network here to get the 12 volts or 24 volts across this here. The ground or common reference is really taken at the midpoint of this was set by these 2 resistors. The original schematic, these were 20 Ks, now I got 33 Ks here. This amplifier is the one that I've read or heard on the internet that has to be a very strong drive, and some people even say they need class B or class AB driver to drive this common, but in my estimation, based on the simulations as well as I tested this thing, I believe even 20 to 50 milliamp output drive is sufficient to make this work. So this amplifier is basically an LM358 in my what I did for making it work. And currently the way I set this up is very crude, and I need to improve the way it's put into the board and how it's actually connected and so on. But just to illustrate that it's working with these two component changes as well as some passive components here. This is a network that generates a plus minus 12 volts. As far as the current is concerned, based on my simulation, I was measuring about 18 to 20 milliamps on these outputs under 12 volt and minus 12 volts. So what this common node has to really supply is the difference in the current that has to go through. It's not the actual full current from the plus 12 and minus 12, because that's provided by the LM317 and this transformer and output DC network. So the difference current here in this case, if it's well balanced, it will be a few milliamps at most. And the way I tested this particular circuit was I applied a single load on each side. I kept one side unloaded, the other side loaded, and I could draw 23 milliamps on this side and 22 milliamps on this side for a 100 millivolt change on the 12 volt supply. That means that any change in the 12 volt supply really results in inaccuracies as well as problems with the main current source network, which depends on this plus minus 12 for various comparisons and various setting various trip points. So here's the 12 volt supply I built on a breadboard just to prove that the circuit would work, and also draw the required amount of current from the plus and minus 12 volt supplies. I'm going to just do a quick test to show you how that works. The inputs are connected down here, 26 volts from a DC power supply, which is about the same voltage the transformer and rectifiers would give on the real 225 current source, and LM317 over here, and LM358 op amp right over here, couple of decoupling filter caps, and the potentiometer to adjust the 24 volts right here. Basically the circuit is as I showed on the board, the same thing here with all the passive components and transistors and ICs here. So let's do a test quickly. So right now the meter is reading 0. Currently I have a 26 volts already supplying the chip. So we'll measure, just the common is the output of the amplifier, which is pin number 1. Pin number 4 should be the negative supply, which will be minus 12. As you can see, it's minus 11.968. And pin number 7 I believe is a plus supply, and that's pin number 8. Okay, pin number 8 is the positive output, and that is 11.991. So basically it's working. I'm not going to show the load test here, but what I did was the two outputs over here on the top just near the capacitor, I was able to put a load resistance, which is a variable load resistance, using a decade box, and I tuned the resistance such that I was getting a 100 millivolt drop on either of these supplies, and like I showed on the board, and arrived at a value of the resistance, which then gave me a value for the current. And based on my simulation of the entire 225 on LT Spice, the current drawn on each of these supplies was around 16 to 18 millivolts. They were about the same. Maybe one of the supplies was a little bit more than the other, but as I said before, the op amp only has to provide the differential current into common, which will be the 0 volts supply. So that concludes this little demo. So in the course of my investigation, I found that this main positive 130 volt transistor TO66 package had blown up, and along with this transistor here below, this Q103 I believe, had also failed. So once I repaired or replaced these two and also did the changes to the 12 volt supply, this whole thing started to work. So at that point I didn't actually take any videos of that, but I did go ahead and try to do some calibration, because I found that some of these values were wrong in the current. They were off quite a bit. So while I was tuning that, it was working fine, but since I can't leave well enough alone, I actually used another current source which had a much stronger drive and tried to stress it at like 100 volts and 10 milliamps or something like that. And unfortunately, during that experiment, I blew up again this thing, and this time it was a different failure. The 12 volt supplies survived this one, but because I had applied a very large current and voltage actively into this one, I thought it would protect itself, but it didn't. I found that this negative pass transistor here and the positive one over here, along with this transistor here, Q104 I believe or something, that one also failed. So I had to replace them with some generic transistors, NP like BC337, BC327 and so on, and that seemed to do the job. And so far I haven't optimized on that. I optimized the actual, try to get the real equivalence, but right now I'm still in the process of getting the accuracy down, and that mostly will depend on the reference voltage and the resistor current. I believe the other values here, or transistors, may more or less affect things like compliance, or where they switch in and out of voltage mode, current mode, which are less critical to me. But eventually, of course, I like to get it, make sure that these transistors are doing the job. And of course, they are rated for the supply, for the currents and voltages, but they may not be meeting the AC specs as originally intended. So the other component I changed was this potentiometer, which is used in the 12 volt network to control the 24 volt supply. So I put in a 10 turn potentiometer there, and this is the other Q104 transistor I believe, which the tiny one. So all these are very susceptible to damage if something fails in the high voltage network. So it's one of the first places to look when something fails in this is to look at this series regulator and also the 12 volt supplies. So here's the inside of the board after the fixes. So this potentiometer here is the one for the 12 volt control, to set it correctly to plus minus 12. These two transistors here and here, Q103, Q106, had blown up while I was doing these various experiments. These two were fine, they never had a problem. The Q102, Q104, which are heat sinked, and I'm surprised they didn't blow up when the main transistor, which are these two over here, the main power transistors, they had blown up a couple of times. So the rest, there was one transistor I believe that maybe over here had blown up, forget that one. And this is the plus minus 10 volt outputs over here. The 12 volts are really right here, plus 12, minus 12. This is the common over here on this resistor. I also replaced these three precision resistors in the decade resistance, 10 ohms, 100 ohms and 1K. I need to replace one more, which is down at the bottom here. It's going to be tough to get to that one. That is 10 mega ohm resistor. So anything that was out of spec I've replaced. As I mentioned, I had burnt one of these during my initial testing and smoked it, and so I think that went out of spec. Besides these, there were no other changes. I will go and show you next the other side of the board, where I temporarily have mounted the series the 12 volt basically the amplifier and the series and the regulator for that. So let's look at the other side. So apologies for this kludgy job over here, but it seems to be pretty well held together, so it's not going to fall off. I think I kind of attached them securely so they won't move around. So this is the regulator LM317, and I basically only needed 3 of these pins out of the original 7 or 8 pins. And this is the amplifier. Again, it had a lot of pins, so just requires a plus minus and the supplies, and basically that's it. There was no need for compensation or any of that stuff here. So these are temporarily mounted. I probably will build a small board and I'll kind of raise it off this board and mount it maybe on the other side once I get it set up properly. Besides that, there was no changes here. At some point I thought on the second attempt, when I blew up the both the transistors, the 130 volt transistors, when I powered on the whole system, it actually was drawing a huge amount of current, almost 2 amps from the supply. At that point I thought I'd blown up the transformer, so actually I removed the transformer and tested it outside, and everything seemed to be fine. So then at that point I suspected other components. Actually there was a transistor that had blown up which I had detected earlier. So once those were fixed, I think everything now is back to functionality, at least. Still remains to be seen if I can get it to the original accuracy. These are the other side of that trim resistor for the 24 volt supply. I shorted one of the resistors out, which is not needed anymore. Yeah, so that's oh, there's one more okay, so there I forgot to mention, I did change the reference generation. So the original schematic showed a Zener diode of I think 6.2, but when I actually went and looked at the schematic, the values were all different. The resistor, that was the fixed resistors, were different, and even the main resistor, which is supposed to be a 4.99k, was not a 4.9, it was 7.87k. So then I recomputed the values. I used a different Zener. I'm sorry, I used the same Zener, but I used a different resistor network to get the same 1 volt, and this time I put in a 7.5k resistor here. This may not be terribly accurate, but for now it's just there. It seems to be, I actually measured this particular value to make sure it is very, very close to 7.5k, and of course it won't be temperature compensated as well as the original one, but for now it's going to do. But with this resistor change and trimming the main potentiometer for the 1 volt, I'm able to get the 1 volt reference correctly now. So that's all the changes and the fixes, and probably next I can show you some results from the final measurements that I've done. Still there are a few more things I need to do, that is to adjust the offsets between the plus and minus, and when I do that I may have to change the gain again, that is to change the 1 volt slightly to make sure it's on target. So let's do some measurements of this repaired unit and see how well it performs with some initial calibration already done. I checked the 12 volts, 10 volts, and did some coarse calibration of the 1 volt and tweaked the offsets also a little bit. So right now the machine is in standby mode. Nothing has been selected here. So let's go to the lowest scale, which is a nanoamp scale, 1 nanoamp. I don't want to go too low because the setup is not good enough to measure in picoamps without too much noise interference. So this is plus 1 nanoamp, and it's not too bad. It's 1.05, 1.06 in that neighborhood. Plus the negative side, yeah, it's minus 0.95. That shows there is a offset which can be probably removed, but I have to see all the different ranges to see how that works out. So if I put in the 0 current, it's in the picoamps, so I'm pretty happy. There's no significant offset here. Yeah, so this could be the offset that could be removed. So let's go to 10 nanoamps. 9 point. It's a bit noisy. Could be my cable as well. Not sure. Nine 9.91. Okay, it's better now. 10.05. 50. Yeah, I'm pretty happy with these type of numbers. I'll probably be operating in these tens of nanoamps and higher. So this looks pretty good. Let's go to 100. This is the 100 nanoamp scale here. It's very good. 100.18, 100.33. So in this particular range, it looks reasonably well balanced on the positive negative side. 400.4005. Yeah, these look pretty nice, good to me, no problem. Let's go to the microamp scales. This is 1 microamp, -1, and it's +1. This looks pretty good. 5. Excellent. Yeah, this is pretty good. Let's go to the 10 microamps, -10.03, +10.025, which is nicely balanced here. Perfect. 20, 20.01. Again, this is perfectly balanced on this scale. So 50 microamps. These are the kind of ranges I would be operating to test a lot of equipment. Looks good. Now if I go into the milliamp scale, that's where I expect some more problems. -1.001, and this is 1.0022. Not too bad. 2.001 -1.988. Okay, and there's 5 milliamps. This is good. -4.996, 4.998. Excellent. And let's go to the highest range, and that's going to be, okay, I've overloaded this machine. Looks like, I think it's 20 milliamps maximum, I'm not sure. 19.993. Okay, it's exceeded 20 milliamps. So I think that's the limit on this one. -19. It's not bad. 18.99. So yeah, I think this is pretty good at this point. I don't know how to adjust this without doing some more detailed resistance measurements to see the different scales, some issues somewhere, but at this point this is a very usable machine. I just need to clean up some of these ICs that I've mounted and close it up, and then run it for a while and check the calibration again. I hope this was informative to some extent. Catch you on the next video. Thank you.